So like Philip said, my name's Josh Winn. I'm currently on the faculty at Princeton, and I started working on transiting planets in 2004, 2005, thereabouts, when there was exactly one transiting planet that had been detected, HD 209458. And even though there was only one detected at the time, it was perfectly obvious that this was going to be a major new field of astronomy with lots of interesting measurements that could be done that had never been done before in the number of transiting planets over the next decade or so, partly due to the launch of the Kepler mission, which had already been planned. I don't know if it was selected at that time, but it was in the air. And then gradually we hatched up the idea for TESS while I was on the faculty at MIT. So my original interest, my original hook, I guess, the way I got into this field was a partnership with Matt Holman, who was a scientist at the Smithsonian Astrophysical Observatory. And he and some others had worked out the theory of transit timing variations, again, looking ahead to the data that we would be receiving from Kepler. The idea that if there is more than one planet around a star and their orbits are close enough to each other that they exert strong gravitational forces on one another every time they make a close approach, then the orbital period of either of the planets would not be exactly constant, and the transits would be a little bit early or a little bit late compared to the expectation based on a periodic schedule. So there were a couple of papers that were published, probably was about 2005, about this, the prospects for detecting transit timing variations. And the exciting thing was that it would allow us to detect lower mass planets than we could have ever hoped for from the Doppler or even the transit method. And it would give us geometrical information that we usually lack, such as the orientation between two orbital planes, or really accurate measurements of the orbital eccentricities of the planets, in addition to being able to measure their masses. So, so we decided to undertake a project using relatively small ground-based telescopes. By relatively small, I mean a meter and a half or so, to obtain really precise light curves of the transiting planets that had started to be discovered and measure the center times of those transits as accurately and precisely as possible, hoping to see these transit timing variations and gain access to this information. Unfortunately, that project didn't work, at least not that particular part of the project, and that's because for a long time the only transiting planets we had were hot Jupiters. And as we now know, hot Jupiters actually rarely have close planetary companions, at least close enough and massive enough to perturb the transit times of the hot Jupiter to a significant, to a measurable degree. So we did lots of other fun things with the data, but we never actually detected any transit timing variations of hot Jupiters. The detections came later when we had transiting planets that were lower mass planets in wider orbits, and those often do come in systems of multiple transiting planets. But what we did do, one of the things we did do, at least one of the things we always wrote in our telescope proposals, was that someday we should be able to detect the orbital period of a hot Jupiter shrinking. And there are various reasons why that might happen. The most kind of a sure thing was tidal orbital decay. The idea that the hot Jupiter is so close to the star that the gravitational tidal interactions between the star and the planet are much stronger than usual. Oops. Sorry about that. They're much stronger than usual, and the long-term outcome is a transfer of energy and angular momentum, well, really a transfer of angular momentum from the planet's orbit to the stellar spin. And as the orbit loses angular momentum, it shrinks. And it's very hard to predict the timescale of that shrinkage because it depends on the frictional processes that take place in the star, which are poorly understood. But it is clear that it should be happening. And based on our best guesses of the timescale, it should take about 10 years, 15 years of monitoring to have a realistic chance of detecting orbital decay. So we wrote this in our proposals that we were setting the baseline for this long-term detection of orbital decay. I'm not sure whether we really believed that we would detect it or that we would still be working in that area 10 or 15 years later. But that is how it panned out. So I remained interested in this field and lots of other aspects of transiting planets But when some of the planets had been discovered 10 or 15 years ago, by 2010 or thereabouts, it did become like a reasonable thing to expect to see the orbital period of a hot Jupiter shrinking. And in fact, there is one such example now where we're pretty sure that's what's happening, and that's the WASP-12 system, which has one of the shortest known orbital periods. It's special in lots of other ways, including the fact that its orbital period is definitely shrinking. So that's pretty cool. And if we had a larger sample of those planets, we could begin to learn about those frictional processes and the tidal interactions between stars and planets, which would itself have lots of other implications throughout stellar and planetary astrophysics. And then, along the way, we developed the idea for the TESS mission, and to my surprise, at least, it was selected and launched. And of course, that gives us an opportunity to be very comprehensive about transit timing, since although the mission was not designed specifically to look at hot Jupiters, it was designed to find smaller planets, it returns fantastic data for hot Jupiters and covers most of the sky. And so the opportunity arose to do a transit timing study of hundreds of hot Jupiters. So that's basically the motivation for this work, is that the data were available, they were high quality, and somebody just needed to go and measure all of the transit times. But it soon became apparent that while that is difficult to write a code to do all that automatically and be very careful about it, I think even more difficult, or at least even more laborious, is getting the transit times collated from the earlier literature dating back to 2000 or thereabouts. Because the standards of reporting transit times have evolved in this field. A lot of people, including myself, didn't really know what we were doing about how to establish a really accurate time system early in this game. And there were a lot of low quality data sets, and we were all underestimating the timing errors and that kind of thing. So a big part of this job is going back through the literature and figuring out which transit times to rely on and which not to rely on, and to impose some kind of quality control, and then combine those earlier transit times with the new times returned by TESS to try to seek evidence for orbital period changes. So here's where I will hand over the microphone to Kate, who will tell us about her work actually executing these tasks.
Thank you. Share my screen. Can you see my screen?
Yep.
Yeah, so my name is Kate, and I'm an undergraduate at Princeton. And so we've been working on this TESS transit timing project for hundreds of hot Jupiters. So we've recently published a paper, and our main contribution is a database of transit times and updated ephemerides for 382 planets. And we use data from the TESS mission and previously reported transit times from the literature in order to create a database. And most planets in the database are hot Jupiters that have been observed by TESS. And so in this work, we had basically two goals. So one was to process TESS data for the hot Jupiters in our sample and update the ephemerides so that people can schedule follow-up observations using this updated precise ephemerides. And the second goal was to provide a database of individual transit times so that astronomers can search for long-term period changes or constrained population level properties from the transit timing variations. And so on this slide, I just show the sample that we had in our study. So on the x-axis, I show the orbital periods, and on the y-axis, the transit depth. And the color magnitude here is the TESS apparent magnitude. And so most planets in our work are short period hot Jupiters with large transit depths. And the gray points here are other known planets that we did not include in this work. So now I want to describe how we created the database. So there were two steps. One of them was to process TESS data, and the second one was to go back to the literature and scrape the transit times from there. So to process the TESS data, we wrote Python code to automatically download the TESS light curves and feed the light curves. And so for this project, we also created a website that I want to show. It's called transittiming.github.io. And on this website, we provide all of our results, the database, the ephemerides, and we also provide an opportunity to look up a specific planet using the search bar. And so for each planet that is included in our work, we provide updated ephemerides, the timing residual diagram, the individual transit times, and also the TESS data that we've processed. And so here I just want to show an example of the TESS data analysis procedure that we used. So here first you see one sector of TESS data for WASP-12. And so the first step in this procedure was to identify the individual transit events in the light curve, which are shown in red here. For that, we used the ephemerides previously reported in the literature. After we identified the events, we phase-folded the light curve and derived the basic transit model parameters, such as the radius, like planet-to-star radius ratio, the orbit-to-star radius ratio, and the impact parameter and the limit darkening coefficients. And after that, we then fitted each individual transit event and extracted the transit midpoint from there. And then we also provide the timing residual diagram just for the TESS data here. And so we did this for all of the available TESS data from all of the available TESS sectors. So after we've done this for about 270 planets, we then went back to the literature and scraped the literature transit times. And so we tried to automate this process because it was time consuming. And so the way we did it is we realized that in the past 20 years or so, like most of the exoplanet papers have been published on arXiv, and arXiv asks authors to upload their source LaTeX files. So we were able to automatically download the source LaTeX files associated to a given target, and then search those files for like the information that we were interested in. And so in this case, for each source file, we were looking for the name of given planets being present in that file, and also a number that is greater than 2 million, which is possibly a timestamp expressed in a Julian date format. So if a given source file passed this criteria, it had a number greater than 2 million, and it contained the name of the target, we would then download the PDF version of that paper, and then we would read it. And so this procedure allowed us to reduce the number of papers that we had to read by a factor of 3 or something like that. And we did not try to automate the last step where we actually had to read the papers because of many practical issues, such as we needed to establish clearly the time system that was used in the paper. Yeah, so these were the two steps how we created the database. And on this slide, I show the chi-square versus the number of degrees of freedom diagram. And on the left, I use only TESS data to create the diagram. And so the gray region here is the region between 2.5% and 97.5% levels of the chi-square distribution. And so the idea here is that if the deviations between our linear model and the data, the transit times, are random variables that are mean zero and normally distributed, we would expect the chi-square to be in this region. And so if we use TESS data only, we see that most systems lie in this region. And so we interpret this as the fact that we accurately assign uncertainties and that there are no short-term transit timing variations in those systems. And if we add literature data, in addition to the TESS data, that's what I show on the right subplot. And so here you see a lot of scatter and a lot of points that lie above the region where we expect the points to be. And this is mostly because the timing uncertainties in the literature are underestimated very often. So now I just want to summarize our results. So on this slide, I show that we improved the precision in the orbital period for most of the planets in our work. So on the x-axis, I show the period uncertainty that we obtain by using literature data only. On the y-axis, I show the period uncertainty from using literature and TESS data as well. And so most of the points lie below the identity line. So it means that we improved the precision for most of the systems. And then after we've created the transit timing database, we then created timing diagrams for each system and search for long-term period changes. And on this slide, I show WASP-12, which, as was mentioned, is the only known system for which we think there is tidal orbital decay. So here you see a clear quadratic trend, and the blue points show the literature data, and the red points are the TESS data that we processed. And the lower subplot shows a zoomed-in version of the TESS data points only. And here I also show WASP-4, which was also previously studied in the literature, and for which there is also a quadratic trend. And in this case, it's mostly due to the line of sight acceleration of the system towards Earth. We then also include a few other candidates for long-term period changes in our paper. And so one of them is WASP-161, where we only have one transit time from the discovery paper, and we include 2 sectors of TESS data. So we see that there are huge variations, but it is possible there was some error in like establishing the time system or something else, like some clock error. And another system that might be interesting to monitor in the future is TRESS-5, where there is also some possible quadratic trends in timing residuals. So we provide, as I said, all of the data on the website. We also provide all of the Python code that we used here. And so we hope that it will be useful for other astronomers in the future for scheduling follow-up observations and searching for long-term period changes. I think that's all that I wanted to say. Thank you.